Hello everyone, this is Charishma. Welcome back to the video lecture on transaction management, that is unit number 6 in database management system. So this unit is all about the concept of concurrency in transaction management. So there's a vital role played by this transaction management in database management system. So let's try to understand what is meant by transaction management first, and then followed by the concurrency condition. So what is meant by the concurrency condition, and let's try to understand whether this concurrency condition is an advantage or a disadvantage in database management system. And if I feel it's a disadvantage, what are the different methods that we have to overcome this concurrency condition or to deal with this concurrency condition? So in those methods, we have something called as locking methods. So what are the protocols we have and what is the role of each type of protocol in handling the concurrency conditions and so on. So let me tell you in detail that you're going to cover the topic of concurrency in transaction management. So one thing I need to make clear is transaction management is a very vast topic, and among those topics, the concurrency plays a vital role. So let's get into a brief discussion on what is a transaction management. So transaction management is nothing but a set of commands, or I can say it's nothing but a small unit of program that you write along with the combination of low-level tasks. So you'll be writing your code or program in which each line performs a small individual task. So I would like to explain the concept with an example. So consider you have two accounts. So hope this example will definitely make the concept clear. So you consider two accounts, account A and B, and you have an operation to be performed on this account A and account B. So what is that? Assume account A is having some 1,000 rupees in it, and I'm supposed to transfer 200 rupees from account A to B. So let's list out what are the set of operations that need to be performed to undertake my main task of transferring 200 rupees from account A to B, which is the one which I'm calling as a transaction. So the first one is, what should I do? I have to check whether there's enough amount present in account A to transfer 200 or not. So in that case, I'd be performing the read operation on account A. And if I'm satisfied with the amount present in A, and if I'm sure that 200 amount can be deducted from A as it is having enough resource, in that case, I go for the next step, that is deduction of amount A 200 from my main account A, that is A is equal to A minus 200. So what is my next step? So once the amount is deducted, I need to read account B. So before that, need to deduct amount, read B. And then I need to credit the amount in account B, that is B is equal to B plus 200. And finally, I write value B here. I write A. So once the amount is deducted and credited into B, I just write A and write B. So if you observe here, I've a set of operations performed to perform my main task of transferring 200 from account A to B. So this is the best example or a simple example of transaction. So let me repeat the definition again. It is nothing but a small unit of a small set of programs that are performed, or small set of program that contains several individual small tasks. Several individual small tasks. So there's one more main, like I can say, this is a unique quality of transaction management. So if you speak about file system, if I start performing the same transferring of amount from account A to B using file system, in that case, assume I have around one, two, three, four, and five, six steps performed for this task. So if in file system even one of those steps fails, assume my fifth step has failed. In that case, I don't have any viability of transferring my 200 back. So there's a chance of inconsistency. So like you may have no idea where this 200 has gone. It has neither credited back to A or nor has been credited to B. In that case, the 200 is somewhere where you don't know. So this leads to inconsistency. But in transaction management system, even if one of those steps from 1 to 6, even one of the steps fails, assume my last step, that is sixth step, has failed. Though my sixth step has failed, I have an enough secured method of transferring this 200 back to account A. What do I mean means, even one of the steps among all the steps has failed, then I have immediately the amount would be rolled back and transferred to account A, and the balance will again turn back to 1,000. So I can see this is one a unique feature of transaction management. And one more thing, any transaction in database management system is supposed to satisfy the ACID conditions. So what is meant by ACID condition? ACID condition, A says atomicity, C says consistency. That means it should not increase any inconsistency in its transfer of data. And then isolation, and then durability. Isolation and durability. So this was discussed in unit number 1 already. So in this transaction management, we'll be mainly looking into the concept of isolation. Concept of isolation. So let's get into the main topic directly. What about the concurrency condition? So what is meant by a concurrency condition, and what is its role in database management system? So what is meant by concurrency condition means a database is supposed to deal with multiple transactions. A database is supposed to deal with multiple transactions. So how would I say it is dealing with multiple transactions? Simple. So you see, no data is static in nature. No data can be static in nature. Always the data or the data element values keep on changing in a database, isn't it? So if you take your banking account, so do you think the details, or a bank dealing with number of accounts having do have the same data all the time? No. Every second the values would be changing because people are working on their accounts from different locations, and the server is busy in updating the values and handling the transactions undertaken by its customers. So one thing is very clear here, that is the data cannot be static in nature. It is dynamic in nature. So when I say word dynamic, then obviously it has to deal with number of commands, more than one set of commands at a period of time. So when it's handling server handling at number of commands at a period of time means it is going to deal with the same different types of operations at a period of time, or I can say multiple transactions at a period of time. So in that case, the server should be capable of handling those operations or transactions in a very effective manner. So it sounds like, is the concurrency disadvantage to a database management system? So let's see. So what would be the answer? So before that, Let's look into the explanation present over here. In multi-user system, multiple users can access and use same database at one time, which is known as concurrent execution. That is what I said. Handling of multiple commands by multiple users in a multi-user system is called concurrent execution. So same data is being executed simultaneously by multiple user system. So now tell me, is this concurrency an advantage or disadvantage? Obviously, I can't say the concurrency is a disadvantage condition, but I should say it's an advantageous condition in a database management system because it is able to handle n number of transactions at a period of time in an effective manner. So if you try to, if you are not able to handle number of transactions at a period of time, so what is going to happen? The work will take enough time. It takes too long for working on an transaction, isn't it? So if, for example, you consider 10 people working at a time on a work, on a piece of work, don't you think the work will be done so easy? Same thing. If the work is have been handled to an individual person on each day and you are waiting for the result, don't you think the time is going to be too long? Same concept over here. So when the server is able to handle n number of transactions at a period of time, it is definitely going to be an advantage. But the disadvantageous condition is about handling the transactions. So need not worry about that. Definitely we have some methods evolved to undertake this condition of handling the multiple transactions. So you're trying to perform the operations or executions happen in such a way that interleaving don't happen. So you see here, simultaneous execution is performed. That is, performed should be in an interleaved manner, and no operation should affect the other execution. So you have certain protocols. Like I can say, you have well-defined rules framed in transaction management system using which the database engine would be able to prioritize the execution conditions of each and every transaction on a data element. So let's get into the concept in detail. Okay. So before getting into the protocols concept, I need to make one thing clear. So what is a protocol I spoke about? Protocol is nothing but the well-defined set of rules which the engine would be using to prioritize the execution of n number of transaction conditions on a data element. So before that, you need to know one thing, that is there are two main operations performed in a transaction, that is read and write operation, like how I've just taken an example and tried to pull out the conditions using read and write operation. Same way, transactions, all the transaction will be having read and write operations on a data element. Okay, so there is a need to manage these two operations in a concurrent execution of transaction. If these operations are not performed in an interleaved manner, like if read and write operations in a transaction management, if they are not performed in a specified manner, or if they are not performed based on the protocols being framed, then definitely it leads to an inconsistency condition. So what is my acid property says about? My acid property says the transaction should satisfy the consistency condition. But if the read and write operations are not performed in an literally speaking in a proper manner, then this leads to an inconsistency condition. Okay, so let's take an example and try to understand what happens over here. So assume I have two set of transactions, TX and TY. And the transaction, all these transactions are happening on an account A. There's an account called as A, and I'm trying to perform the transactions. There are two types of transaction, TX and TY, on the same account A. So what is at first I'm doing? I'm trying to check the balance of account A. So how much is the balance written over here? So around $300. So first I need to read the amount present in account A, which is how much? $300. And now I'm trying to deduct 50 rupees from this one. And if you observe here, 50 rupees when it is deducted, my balance should be 250, isn't it? So what is happening over here in my next transaction, before this is being committed? So once the read operation is performed and $50 has been deducted from account A, it has to write and commit the amount. What is this commit going to do? Commit is going to save the final transaction value. But do you find right over here? No. So this transaction is followed by one more read operation A. So as the commit is not allowed over here, as the commit has not been done, what is it going to read here? You see, this 250 will be only saved when you give write command over there, but the write command is not present here. In that case, read operation in my transaction TY is going to read again 300 rupees. It's going to read again 300 rupees. It's not going to read 250. It's going to read 300 because 250 is not being committed by write statement. So once this 300 is again read, there's one more transaction happening. I've added that 100 rupees to the same 300, and my account A here is holding the value of 400. So if you observe here, the as this is not being followed by again write commit statement, A is again holding 400 values, and in this case A is holding 250. So don't you think there's a dynamic condition? I mean, there's a dynamo existing for account A, whether it is 250 or 400, isn't it? Because the write statement is not executed over there. Now you see, once this transaction of 400 is over, and again transaction TY started writing. So what did you observe here? Before the write statement has executed, read has been also executed. So between this time period between T2 and T6, T3 and T4 happened, which has credited 100 rupees. So you try to assume what should this write value commit. So this write value of transaction TS is going to commit 250, and you observe here TY is going to commit 400. So what should be the final value of A and A? Is it 250 or 400? No idea. So this has led to a very inconsistent condition in the transaction. So that's why there's a clear statement given over here, that is both the read and write operations has to be managed in an interleaved manner. It has to be managed in a proper manner. Read and write operation should be very cleverly handled. It should be handled in a very clever way. So this clever way of handling read and write operation can happen only using the protocols. So I think you got enough idea about the protocols, why you need a protocol, and what happens if you are not making your read and write operations in a proper sequence. So that's very clear from this example. Let's proceed. Get into the concept of locking protocols. Okay, so among these protocols, what I spoke just now, my first type of protocol is the locking protocol. Locking protocol. So what does the name says? Locking. So locking, it doesn't mean that you're locking something and nothing is being performed over there. So this is something little different and try to understand. Okay, so take a data element, assume a data element X. So I'm naming a data element. So this data element can be anything. It can be a table or it can be a file, whatever it is. So this data element X, for suppose I've locked this data element, for suppose I have locked. So what happens if I lock the data element? So when I lock a data, any data element, then I got permission to perform read or write operation. Read or write operation. So I'm trying to explain again. So when I lock any data item, it means that I received permission to either read or write on the data item. So I can read the value of the data item, or I can even write anything on the data item, or I can commit the values in the data item. What does it mean? When you have, for example, n number of data items, x1, x2, x3, x2, x3. Among this, assume I have logged only x2. In that case, only x2 can handle the operations of read and write operation. If the lock is not imposed on any of the data item, then read or write is not allowed on those if they are not logged. So simple it is. So let's try to understand very detailed over here. One of the methods to ensure the isolation property in transaction is to require that the data items be accessed. Data items be accessed in a mutually exclusive manner. So what is that mutually exclusive manner? Let's try to understand. So this exclusive condition would happen only with the locks. So the most common method used to implement this requirement is to allow access to the data item only if it is currently holding the lock. So holding the lock is very, very important in order to make a transaction happen. So clear it is. Let me repeat. Holding the lock is very, very important to let the transactions happen on any data item. It can be read operation or write operation. So the lock-based protocol is a mechanism in which there is an exclusive use of locks on the data item for the current transaction. Let's try to understand the concept in little detail in the coming slides. Okay, so here is the slide. So what did I do here? I've just segregated the concept of locks into two. So I have two types of locks that can be imposed on a data item. The first one is a shared lock. The second one is exclusive lock. So there's a purpose for each type of lock. So if you are imposing shared lock on a data item, there's a set of operation that can be performed. For example, if I impose exclusive lock on the data item, there's one more set of operations that can be performed. Let's try to understand the significance of each type of lock in the locking protocol. The first one is the shared lock. The first one is the shared lock. So the shared lock is used for reading the data items only. Make the concept very clear. So what is the use of the shared lock? The shared lock is used for only reading purpose, and it is denoted by S. It is denoted by S. So as I'm saying, it's going to allow only the read operation on the data item. I can give the other name to the shared lock, that is read lock. So this shared lock can be otherwise called as the read lock. Okay. So next one is exclusive lock condition. So this exclusive lock would be allowing me to perform both the read operation as well as write operation. And how to represent an exclusive lock? I represent exclusive lock with the capital X. And the other name of the exclusive locks is nothing but the write locks. So shared lock is represented by S and exclusive lock is represented by X. Okay, so there's a question: if I have a data item, if which is being imposed by one type of lock, And on the same data item, there was a need for imposing one more lock on it, isn't it? So this happens. Transaction is nothing but dealing with different types of operations. In that case, when I have one lock imposed on data item, there might be a chance of imposing one more lock on the same data item. So what categorization or what priority the database engine should take care of this in this condition or in this scenario? So to decide which one to be allowed and which one to be rejected, or which two combinations can be allowed or which two combinations to be rejected, we have a compatibility matrix which is being followed by the engine. Okay, so you observe here, so I have a compatibility matrix of the shared lock and exclusive lock. So one shared lock and one exclusive lock. So I'm trying to find out the possibilities of different combinations on the same data element. Okay, so for example, a data item is having the shared lock imposed on it already. Then in that case, it can also allow one more shared lock condition because it says true here. The combination of S and S is saying true. What does it mean? When a data item is having a shared lock in it, then the other transaction on the same data item can also impose shared lock. So why? It's all about read operation, right? So when the data item is locked with read operation, then obviously the other transaction can also read it. There's no question of overwriting. So reading can be easily allowed over there. So let's try to understand the same compatibility matrix in a detailed manner. So you see, if transaction T1 is holding a shared lock in the data item, then control manager can grant shared lock to transaction T2 also, isn't it? That's just now what we have discussed. And same way, but it cannot grant exclusive lock as the compatibility matrix is false. You try to understand. So for example, the transaction T1 is having shared lock. The next transaction can handle shared lock again on the same data element, but it is not going to allow exclusive lock. You see here, exclusive lock and shared lock combination has set to be false. That means on the data item having a shared lock, exclusive lock in the next case or in the next transaction, the exclusive lock will not be allowed. Same way, if transaction T1 is reading the data element A, then the same data item A can be read by another transaction. So this was also discussed just now. Okay, let's proceed. What happens if this data item has already an exclusive lock imposed on it? What happens if it is having an exclusive lock already imposed on it? So you see, when a data item has an exclusive lock imposed on it at transaction T1, and there's one more transaction T2, which can either have a shared lock or an exclusive lock, which can either have a shared lock or exclusive lock. In that case, it is not going to be compatible. So if my first transaction is working on the shared exclusive lock, and my second transaction on the same data element is trying to impose either shared lock or an exclusive lock, in both the cases, the compatibility is going to fail or it's going to be false. That means one transaction is writing the data item A, then other transaction can't read or write the data item. So what is happening when I'm imposing exclusive lock? It means that there's some operation happening on data item. So when the operation is happening on data item, there's definitely no chance of reading the concept, isn't it? So it's like something you're writing your exam. So before itself, I'm trying to assume the result of yours. Is it possible? Not at all. So you have to write your exam and submit it, and there's the correction has to happen. Then only I can read your marks. So that same way, when the process is happening, definitely your committing of the value, final value cannot happen. Okay, so all this compatibility matrix what we have studied can be simply taken in two thumb rules. First one is any number of transactions can hold shared lock, isn't it? So if I'm imposing shared lock on a data item, on that again I can impose a shared lock by next transaction. Again I can impose one more shared lock on a next transaction. So I can handle n number of shared locks on a single data element. Okay, so in this is not the case in other type of lock, that is exclusive lock. In exclusive lock can handle, can be held by only one transaction. So that means once the exclusive lock is imposed on a data item, no other type of lock can be overwritten on this data item. So simple it is. So why I've taken this concept in a detailed manner is this is the same concept would be explained, or it is little extended in the coming slides. So once you understand this one in a clear manner, we'll be able to understand the coming concepts very easily. Okay, so my first next type of protocol. So just now we studied about locking protocol, right? Now we are trying to study about the time-based protocol, timestamp based protocol. So again, this is very important and is going to play a very key role in handling the concurrency condition. Let's see how. Okay, so in this timestamp based protocol, we are trying to we are trying to impose values on each transaction, impose values on each transaction. So why I need a timestamp based protocol? So what is the use? So let me tell you in very simple manner. It is going to tell which transaction has to be executed first and which has to be executed next. So simple it is. This timestamp based protocol will help me in deciding which one should be first and which one should be next. So how was this decision of deciding which one should be first and which one should be next made? So that decision is made this way. Okay, let me take an example again to make you understand that. So I have a data item X, and on the same data item I have two transactions happening. So transaction T1 and transaction T2. So you you try to see in transaction T1, I'm writing a value over here. So let it be 1 on second transaction value be 2, or let it be 10 on the second transaction value be 20. So I've just taken some integer values, or I've just fixed some integer values on each of the transactions. Now find out which transaction is having least value. So obviously transaction T1 is having least value, that is 10, and transaction T2 is having highest value, that is 20. So what is this going to tell me means it is going to tell me that transaction T1 has happened first because it is holding the low value, and transaction T2 has happened next to T1 whose value is 20. So what does it mean? The transaction which is holding least value is said to be the older transaction, and the transaction which is holding the large value is said to be the younger transaction. So first transaction 1 has approached the data element and followed by transaction T2. How did you find this one? Based on the values that has been inserted for each transaction. So the values what I'm speaking here that has been inserted to T1 and T2, these values are called as timestamps. These values are called as timestamp. So as the name says timestamp, it doesn't mean that you're trying to put only the timing on the transaction. So of course, if you want, you can also store the time for time of transaction. So for example, my first transaction has happened at 10:10. So my second transaction has happened at 10:20. So I've tried to replace the integer values with the time. So this is also one of the methods that through which you can say which one is older and which one is new. And Apart from this timing, you can also fix the integer values. So that's okay. This integer value is also one of the best methods to say which one is older and which one is new. You don't bother about how you are trying to impose the stamping. You just bother about which one is the less value and which one is the highest value, and the one which is holding the less value set to be the older one, and one which is holding the large value set to be the younger one. So now you try to analyze, when I have two transactions, old and young, which one should be given top priority? Which one should be top priority? If I'm not wrong, you would be thinking older one should be given top priority. And you are right. The first one, that is older transaction, should be given first priority. Once the transaction T1 has finished, or once the transaction of T1 is executed, then only the younger transaction is given chance to execute on a data element X. So once T1 is over, then only T2 can proceed to execute. Okay, so again we are trying to impose the read and write operation conditions to the timestamping. Okay, so when I have an indication of RTS, when you find something called as RTS in bracket X, it means this is the timestamp value when the last read operation has been performed on an object X. And same way, when I have WTS, this means this is the timestamp value on an object where the last write operation has been performed. So when did the last write operation happened? So that will be mentioned in WTS, and when did the last read operation has happened? That will be mentioned in RTS of X. And what is this X? X is nothing but the representation of data element. So in turn, this is something something which is helping you to decide whether the transaction should happen or abort, whether the transaction should happen or abort. So for that, again, you have a set of rules that has been framed in timestamp ordering. That is, you have an algorithm that you follow over here, which help you in deciding whether a transaction should be proceeded or it should be cancelled out. Okay, so let's see what is this algorithm about, and what are the different case studies we have, under which condition the transaction will be proceeded and on which condition the transaction will be failed. Okay, so you have two different cases in which there are again two set of conditions given there, and each condition will be guiding the engine to either proceed or abort. Okay, so let's not explain it, and let's proceed. So to understand this timestamp ordering algorithm, what you have to do is you first consider TS. You can first consider TS. So what does it mean? TS is something which is performed a transaction, the timestamp of either read or write operation. So I'm not clearly mentioning whether it is for read or write. You just assume TS of X is nothing but the timestamp value of either read or write operation. So this read or write will change according to the cases. Okay, what happens if I'm considering read and what happens if I'm considering write is what you're going to study over here. Okay, so what is my case 1? So what happens if the timestamp value is higher or lower? What how it proceeds? Okay, so this is quite interesting topic, and try to understand the concept in detailed manner. Okay, so first case is for the read operation. First case is for read operation. So try to understand, if in case my last read timestamp, so TS of T in this case 1 is for read, right? So I already said here it can be read or write. So for my case 1, it is read operation. So the last timestamp value or latest transaction timestamp value for read operation, if it is less than the write operation which has happened at the last. Okay, So the latest read operation timestamp value, if it is less than the write operation timestamp value, in that case read should be rejected. Read should be rejected. That means the transaction has to abort. Okay, so this case will be again much more clear with the example over here. Okay, so consider the example. I have transaction T1 and transaction T2 with the timestamp value 10 seconds and 20 seconds. Okay, so here the latest read operation, that is TS of X. The TS of X is nothing but R of X, isn't it? So for case 1, TS of X is nothing but the read operation you see here. So my latest read operation timestamp value is less than write operation. So can it happen? You see, when write operation is happening, after the read statement, can I read the value before the operation has performed? Definitely not. Definitely not, because the read operation what I'm speaking about here is having timestamp value 10, whereas write operation is happening after 10 value, that is at the 20. So unless and until the write value has not happened, the read cannot be performed, because though if it performs, it is going to give you a very false value, because you don't know what exactly happened on this data element after the read operation, because write is going to say that. But you're not allowing the write to complete its work. Instead, you're trying to read it before the write operation has performed, so which will fail. Okay, same way, go to the next case, next point of case 1. That is, if the write operation timestamp is less than the latest read operation, in that case it can read it. Isn't it? It is quite opposite to the previous case just now we have studied, right? So what happened here? So you are trying to read it before the write operation is being completed, but here the timestamp value of write operation is 10 seconds. That means it is happening first. The write operation is happening first, and the final value of X is being committed in the write operation. So once this commit happens, then obviously you can easily read, or you can read the right or exact value of R, or I can say you can read the updated value of the data element X after the transaction T1 at 20 seconds, because at 10 seconds the write operation has committed the value, and at 20 seconds you are trying to read the updated value. In that case, the operation or the transaction is accepted. So this is about case 1. Okay, let's try to understand case 2, where the transaction TS of X is a write operation. Okay, so let's analyze. If write operation timestamp is less than read operation timestamp, if write operation timestamp is less than read operation timestamp, or the write operation timestamp is less than again write operation, then write is rejected. Same case. So when the write operation is happening at greater timestamp value, then you can't work on it before it finishes its work. It can be read or write, don't bother. So none of the actions, either read or write operation, cannot be performed before this write performs its work, because its timestamp value is greater compared to R of t. So let's try to understand here using an example. So the write operation that is being performed is 20 seconds, and the latest write operation happened at 10 seconds. Definitely this can't happen, because once this is completed at 20 seconds, after that, at the greater timestamp value, it has to write again on data element X. But it cannot make changes on the write operation or transaction T2 final value of transaction T2 with less timestamp value. It cannot make changes on that because the timestamp value is less. Okay, so let the operation perform, and then at the greater timestamp value, you can perform the next W of X. So in this case, it is going to fail. So next one, if the write timestamp of data element is less than either read or write, or if the write timestamp value is read timestamp value is less than the write timestamp value. So what is going to happen? So it is going to execute the write operation. Why? Because once the write operation is being performed and it is committed, then obviously it can encourage the next write operation. So quite opposite to this case. Okay, so if you observe here, though I have mentioned two separate cases in separate conditions in each case, actually they are working opposite to each other. So if you try to understand the first one, you will be able to understand the next one as well. It is vice versa. Okay, so this is all about time stamping protocol. So far you studied about locking protocol, and now you have studied about timestamp based protocol. Okay, so next one is multiple granularity. Multiple granularity. If you remember, while explaining the concept of locking protocol, I said the concept will be little extended in the coming slides. So that extension topic is about the multiple granularity. That topic is about the multiple granularity. So what is this multiple granularity about? So it's all about the hierarchical breaking of the database. Hierarchical breaking of the database. What does it mean? So you're trying to break your database, complete database. You know, the database is such a huge structure that you can't handle all the conditions on the, like, you're trying to work on a huge element at a period of time without categorizing it. Do you think it will give you an effective work at the end? Definitely not. So instead of that, you better segregate your huge database into sub elements, or you try to categorize that one in the form of subcategories, and those subcategories into again subcategories. So what is that you're doing? You're trying to break your huge database into blocks. Okay, so why you have to break this one? In order to determine, or you in order to maintain a hierarchy, which one should be first and which one should be the next one, which one is given top priority and which one is given low priority. So you're trying to create a condition, hierarchical condition over there. So what happens is, once you try to break your database, the locking concept would be much easier. So again, you have set of conditions over here where you impose lock at one element, and it is going to impose this lock on sub elements as well. Okay, so let's get into the multiple granularity concept in a in little detail manner. So what is that you're going to do is, you're going to break your database in the form of a tree. So this tree consists of nodes. This tree consists of nodes, or I can say the database you consider as parent, and the subcategories what you have for this database are called as children. Okay, so the link existing between, or the junction that links up both the parent and the child, or this junction that is created at each point, is said to be the nodes. Okay, so this I can explain in little better manner in the coming from a diagram. Okay, so before that, let's make the concept little more clear. Multiple granularity protocol enhances concurrency and reduces log overhead. Lock overhead. That means the systematic locking approach will be encouraged in multiple granularity concept. So it maintains a track of what to lock and how to lock. So which one has to be locked first, and how is it going to affect the other locks? So is there any chance of is there any need of locking the other children also? So these are something which is going to be studied in the coming slides. Okay, so let me try to explain you the multiple granularity within a diagram. Okay, with a diagram. So the topmost category of any database would be any representation in the multiple granularity would be database. So this database is again splitted into sub-databases based on the areas. And these areas are again splitted in the form of files, and each file is being segregated in the form of record. Okay, I can explain this one with a simple basic example. You assume there's an institution, there's some institution, and this institution is holding its own database, or it's having a very huge database of itself. That means it's a combination of all the data relevant to the institution. Is it easy to work on the huge or bulk complex database directly onto the institution database? Definitely not. So to overcome that condition, what did we do? We just segregated that institute main database into two conditions. So it can be based on the departments, let me take. So one area can be EEE or one area can be CSE. So based on the departments of the institution, I have segregated my database based on the departments. One can be department EEE and the other one can be CSE. And in this category, I have again the records. This database of EEE can also again categorized based on faculty and students. Faculty and students. And again, the faculty records. So for you assume there are about 20 faculty working in EEE department. Each faculty would be having his own record, right? So that means R1 to R20 records are present under faculty database. Same way, students, you assume there are 60 students studying over there. In this case, there are 60 records being maintained under student category of EEE department in an institute database. So simple it is. So what is that you're going to do? You're trying to split out your main database in the form of a hierarchy. So this one is called as parent and these are called as children. And these nodes which are formed are the points where the locks are imposed. So in this multiple granularity, you will be trying to impose locks on the nodes and try to see what is the effect of imposing lock on each of these nodes. So in my previous explanation about locking protocol, I spoke about two locks over there. One is shared lock and the other one is exclusive lock, isn't it? So apart from the shared and exclusive lock, we are adding three more locks over here in the multiple granularity concept. The first lock is intention shared lock, and next one is intensive exclusive, and last one is intensive shared intention exclusive lock. Okay, let's see what is each lock about. So when I try to impose intention shared lock, it means that locking at the lower level of the tree, but only with the shared lock. So this is nothing but you are trying to lock the lower level of the tree. Which is the lower level of tree? That is records. So this intention shared lock can be imposed on the lower level of the tree. Imposed on the lower level of the tree, and this lock will encourage only shared conditions in the records point. Okay, next one, intention exclusive lock. So this contains explicit locking at the lower level with exclusive or shared lock. So when I impose intention exclusive lock, that means again this is imposed on the lower level, and this encourages either exclusive locks or shared locks. Okay, and the shared and intention exclusive lock is something combination of both. In this lock, the node is locked in shared mode and some node is locked in the exclusive mode by the same transaction. For the same transaction, each node is being locked by two different types of locks. One is shared, the other one is exclusive. So try to keep in mind all these locks what I spoke about, that is intention shared, intention exclusive, or shared intention exclusive. All these are imposed on the nodes. At which level of nodes? That's what we have spoke about. When I speak about intention shared, it is going to encourage only shared lock at the lower level. Intensive exclusive, it is going to allow both intention and shared lock. I mean shared and exclusive lock at the lower level. Okay, so when I speak about locking condition, obviously it comes and reaches a point of compatibility matrix again, because each data element is might comprise of different transactions at a period of time. In that case, this compatibility will help in deciding which one to be proceeded and which one should be aborted. Okay, so again the compatibility matrix goes something like this. So intention shared locks, combination of intention shared lock with the other locks will go fine, except for shared exclusive lock. Okay, and intention exclusive lock except for shared intention, shared exclusive, and exclusive remaining all, it will go fine. Okay, so from this compatibility you can make an analysis, and let me bring out the key points from the compatibility matrix directly. The first one is the transaction T1 should follow the log compatibility matrix. So these are the rules that need to be followed. And next one, so obviously it has to follow the log compatibility matrix first. And next one, transaction T1 firstly locks the root of the tree, then it can lock it in any mode. So once it locks the root of the tree, so root of the tree means, so if for example DB is directly locked, then obviously when parent is locked, obviously the children can be locked, right? So that's what it says. Firstly locks the root of the tree, then it can lock it in any of the modes. And then T1 currently, if T1 currently has the parent of the node locked in either, if the parent is locked in either intention exclusive or intensive shared mode, then transaction will lock the node in either shared or intention mode only. So you need not bother about this complete sentence, just make the concept very simple in mind. So if the parent is provided with IX or IS, then obviously the child should be allowed only with S or IS mode only. Next one, if T1 currently has a parent node locked in either, so if the parent node is locked in either IX or intensive shared intensive exclusive mode, in that case the child would be allowed to lock a node, then the transaction will be allowed to lock a node in either X or SX or IX. So these are all obtained from the compatibility matrix. So, and third rule says if T1 has not previously unlocked any node only then the transaction T1 can lock a node. So for example, there's a transaction which has not logged any of those. So always the lock was imposed and it has not unlocked once the transaction is done. In that case, the transaction T1 will continue to lock the node. So one thing should be kept in mind when you are trying to lock any data element to perform any activity. Once the activity of read and write operation is over, immediately it has to unlock the data element so that the next transaction can undertake that. Okay, next one. So this is all about the protocols what we have studied so far. Now we'll be looking into the most and very crucial element of transaction management, that is deadlock condition. Deadlock condition. So again, this is one of the aspect which is helping to deal with the concurrency condition. So concurrency condition means dealing with n number of transactions at a period of time. So how to prioritize the transactions? So just now you spoke about protocols. Apart from the protocols, you have something called as deadlocking. Let's see how this deadlocking going to help you in dealing with concurrency issues. Okay. So let me explain you in a form of a small story, okay? So what is meant by deadlock? So I have, for example, there are two friends. friend A and friend B, and unfortunately they had a fight between each other. And this A thinks, let B come first, approach me first and speak to me. And B waits for A to approach him first. And A waits for B to approach him first. So there's something like an ego clash existing between A and B. And this is never going to end, because this is waiting for B and B is waiting for A. So this is a never ending process. This is happening in a cyclic manner. Do you think the quarrel can end up somewhere? No. So when can the quarrel come to an end? Unless and until one should leave his ego and proceed to speak to the next one. Same way here, in the concurrency condition, the transactions happen in such a way that the first transaction T1 will be holding the lock on a data item. The second transaction T2 is holding one more data item. And this transaction T1 need to proceed for the next data item X2. But this X2, this T2 is not releasing the data item X2 for the transaction 1 to complete. On other hand, T2 is not releasing the resource to complete transaction, to allow transaction T2 to complete. So let me make things clear. The T1 is waiting for T2 to release the resource so that it can finish off its work. On the other hand, T2 is waiting for T1 to release the resource so that T2 can finish first, which is not at all happening in either way. In that case, a lock has happened, which is leading to a dead condition of a transaction. So this dead condition of transaction is called as deadlocking. Dead condition of transaction is called deadlocking. So I have an example here, you see. So there's a student record and a grade sheet record, and this transaction is holding the student data, locking the student data. So holding in the sense it is locking the student data to make either read or write operation over it. And on other hand, it is also sending the request to one next data item called as grade sheet to complete its transaction. So why is it sending a request? Because it is this grade sheet is being already holded or locked by one more transaction T2. So you see the activity of T2 over here. On one hand, it is holding the data item or locking the data item called as grade, and on other hand, it is sending the request to the student. So don't you think it is happening in a cyclic manner? If I want transaction T1 to complete, T2 has to release grade, or if the transaction T2 to be completed, the student the student data item has to be released by transaction T1, where both of them are not releasing their locks on the respective data item. So this leads to deadlock condition. So there's a chance of occurrence of deadlock in the concurrency. So when the deadlock happens, the transaction can neither move forward nor come back. It will just stuck and the database will stop working. So this is something which leads to an inconsistency condition in the database operation. So how to deal with this deadlock? Okay, so one thing, keep in mind, deadlock is something which is rare to occur, but there's a chance of occurrence. But once it occurs, it leads to a big issue. So there's what we have to do is we need to analyze the elements before itself so that we can avoid the data deadlock conditions. So the proper care has to be taken at the initial stage or the schema level itself, and check whether this leads to deadlock or not. Okay, so background work will be first done and then only the main programming happens or will be planned. Okay, so what are the necessary conditions on the deadlock occurs? So what are the different conditions that leads to deadlock? Let's see. The first one is hold and wait condition. So this is something which is going to happen, which leads to the deadlock condition, hold and wait condition. So what is happening here? So I have P1. P1 is holding, so P1 is a transaction and this is holding the resource R1, and on other hand it is sending request to R2, like how we have seen just now. So that is something called as hold and wait condition. Next one is mutual exclusive condition. So what is this mutual exclusive condition? So this was also explained in the previous example. So there are two transactions, P1 and P2, and this P1 is holding resource R1 and at the same time it is sending request to R2, which is being locked by one more transaction called as P2. Okay, so what does it mean? There must be at least one resource that cannot be used more than one process at a time. But what happens here? This resource R2 is dealing with two types of transactions, that is T1 and T2. One is the request one, the other one is holding, which should not happen. So when this condition happens, this leads to deadlock. Okay, next one is circular wait condition. So what is a circular wait condition? So the request and waiting happens in a cyclic manner. Okay, the condition where one process is waiting for the resource that is being held by the second process, and second is waiting for the resource that is being held by the third process, and so on. So first is waiting for the second one, and second is waiting for the third one, third is waiting for the fourth one, and so on. And again it comes and meets to the first element again. That means this is forming a cycle or a loop. So when this looping type of requests and waiting happens, this leads to deadlock again. Okay, next one is about no preemption condition. So what is this no preemption condition? A resource cannot be forcibly taken from a process. So for example, as a data element X, so I'll be again every time in this complete lecture when I speak about X, this is nothing but the data element. So this data element X, when it is being holded or locked by a resource, then obviously it should not ask, or one transaction should not force this data item to be released. Okay, so if for example T1 is holding the lock on data item TX, then the T1 has to voluntarily come forward and release the data item for the next transaction. This is called as no preemption condition. Okay, so let's see various methods to handle the deadlock condition. The first one is deadlock avoidance. Deadlock avoidance. So what happens means when the database is stuck in a deadlock, so we feel like it's better to avoid the deadlock rather than restarting your database. So when you feel like your database is small and is not holding a very crucial data in that, and it's okay if the database is again restarted or if I delete the database if the deadlock occurs, because I can again handle the data present in it. If you're confident enough with that one, you need not break your head to handle the deadlock. Instead of that, you can just abort your database, then the deadlock will be obviously vanished. So this is one deadlock avoidance condition. So next one is about deadlock detection. So what is this deadlock detection about? So you're trying to identify or make a prior analysis whether there's a chance of occurrence of deadlock or not. Okay, so when a transaction waits indefinitely to obtain a lock, the database management should detect whether the transaction is involved in the deadlock or not. So for example, you feel like there's one transaction happening and transaction happening where one transaction is waiting for a long period of time for a resource to be released by the other transaction. If this long waiting is happening, you have to check whether any deadlock has occurred or not. Okay, so for this, you have one method called as wait for graph method. So this is one of the methods for detecting the deadlock situation. So what happens means you will be trying to draw a graph and graph between the wait and hold conditions of transactions, and if you feel like a cyclic loop has occurred, then that means there's a chance of occurrence of deadlock. Okay, so next one is deadlock prevention. So let's see how to prevent the deadlock. So what happens if the deadlock occurs. So usually deadlock prevention is something that happens or that is taken care in a large database, because there you don't have any option of deleting your database, because large database means it would be definitely handling crucial factors in that. It should be definitely taking out the crucial elements. So in that case, you have no option of deleting the database. Instead of that, you have to work on overcoming the deadlock condition. In that case, the first one is wait to die condition. So the concept will be very simple and interesting. Let's try to understand. So if the transaction requests for a resource that is being locked by the other transaction, then the DBMS simply checks for the timestamp. So this complete deadlock prevention condition is about checking the timestamp values. So this timestamp values will guide you in deciding whether the transaction has to be processed or which one should be avoided. That means I spoke about two friends, right? So there's a parent-like condition who came and decided whether who should talk and who should stop talking. Okay, the same one here. So let's try to understand wait die condition. So there I have two scenarios. First one, you have to check whether the transaction timestamp value of T1 is less than the timestamp value of T2. So if timestamp value of T1 is less than timestamp of the value of T2, first find out which one is older. So when I say that T1 is having less timestamp, then obviously T1 is said to be old transaction and T2 is said to be the new transaction. If T1 is older transaction and T2 is held some resource, in that case, T1 will be allowed to wait. So the priority will be given to T1 and it says wait for some time till T2 finishes off its work. That means you are giving a chance for T1 to wait for some time. But if it is opposite, that is, if the time period of T1 is greater than time period of T2, then T2 is said to be, if time period, if it is opposite, what is happening? T1 is an older transaction and has held the resource. So you see, T1 is old transaction, it is having control over the resource, and T2 is waiting for the same resource to be unlocked by T1. In that case, as T2 is a new transaction, so the engine says you abort yourself. You cancel yourself and wait for some more time till T1 finishes its work. Whereas in previous case, as T2, which is new transaction, is holding the resource and T1 is waiting for the resource to be unlocked by T2. T1 is old, right? So priority will be given for T1 and the engine says, okay, you wait for some time till T2 finishes his work. If the case is opposite, where T1 is holding the resource and T2 is waiting, in that case, T2 has to kill itself. Okay. And after some time, it has to start again with the same timestamp. So it takes a time and then again restart. So in simple, I can say this scheme allows the older transaction to wait but kills the younger transaction. So simple it is. Okay, priority is given for the older transaction. The next one is wound wait condition. So what is this wound wait condition about? If the older transaction requests for a resource held by younger transaction, then old transaction forces the young transaction to kill the transaction. So that means it is almost similar to the previous one, but the difference is in previous case, the T2 was dropping itself from the transaction because the T1 is holding the resource and it is been waiting and T2 is waiting for a long period of time. So it drops itself because it's a young transaction. In this case, in wound wait condition, in case if T1 is waiting for the resource that is being held by T2, it directly forces T2 to kill itself so that it can proceed. Okay, so what happens to the young transaction once it is been forced to be killed? The younger transaction is started with a minute delay with the same timestamp. So it gives some time for itself and again occurs. Okay, this ultimately prevents the deadlock condition. So these are the two interesting cases what we have studied, that is wait die condition and wound condition. So these are all the concepts of data, important concepts of concurrency condition in transaction management. Hope you enjoyed the video. Thank you very much.